The broadcast is now starting. All attendees are in listen-only mode.
Good morning. My name is Mindy Reyes. I'm the Managing Director at Salford Systems. Thank you for attending our webinar. Today's topic is 3 ways to improve your regression. Our presenter, Caitlin Ontank, is Salford Systems marketing statistician whose key responsibility is helping end users of all levels to optimize their use of data science technology. She's a graduate of UC Berkeley's master's program in statistics. You will have an option to submit questions throughout the session, and we will answer every question, if not during the Q&A, then within the next few days. Please welcome Caitlin Ontank.
Hi everyone, thank you for joining us for 3 ways to improve your regression. Today, for about 45 minutes, I will be showing you 3 fast and easy solutions to get a better model than your typical baseline regression model that you may be running now. So first, a little bit about the company for those of you who don't know who we are. Salford Systems is an advanced analytics software development company. We were founded in 1983. We are known as the company that brought the world to cart decision tree and TreeNet gradient boosting. Our tools are based on the original research of scientists that invented the most important algorithms in machine learning. And we have documented advantages in computational speed and accuracy over some of the other platforms that are out there. So just a quick outline of what I'm going to be showing you today. First, I'm going to go over some of the issues that you may come across in a standard linear regression. And then I'm going to talk about the 3 solutions that we have for those issues. And that is Mars, TreeNet, and Random Forest. And I'm going to talk about how those tools can solve the problems that you might be coming across. Then I'm going to do a hands-on demonstration. And this webinar is going to be more of a demonstration than going over the actual theory behind these solutions. And finally, I'll be talking about the results and some of the other applications of these models. So some of the issues that you might find in regression are missing values. And this happens a lot in real-world data. And typically, you would just be deleting these records. And this can be a huge problem because you lose a lot of your training data if you're just deleting every single record that has a missing value. Or if you're trying to do imputation by filling in the values yourself, this could be inaccurate or it could take a long time. You also might encounter some nonlinearities. And this is a problem in linear regression because linear regression is capturing the global effects of your model and ignoring the local effects. And this might require some manual transformations, and it's just a pain if you're trying to capture something that the regression just isn't looking at. Another problem is interaction. Sometimes you have to add these in yourself. And finally, variable selection. If you have thousands of predictors and you're not sure about which ones you want to put in your model, or you're trying to decide what p-value level you're going to look at to choose your variables, it can just be a lengthy process. And I'm going to show you how our software does that for you automatically. So these are our 3 solutions, Mars, TreeNet, and Random Forest. And these 3 address all of the issues from the previous page. It does automatic variable selection, automatic missing value handling. It allows for nonlinearities and interactions. And just because I say this is automatic, it doesn't mean that you have no control over it. There's still room for user intervention. You can still decide which variables you definitely want in the model or which ones you definitely want to take out. And you can also decide exactly where you're going to be imposing nonlinearities or interactions. So it is user controlled, but it can be automatic if it's not something that you want to do yourself. So we're going to get to the data now. The data set I'm going to be using today is a publicly available data set, and it's an application in civil engineering. A professor from a university in Taiwan wanted to figure out what kind of materials would make the strongest concrete. So our target variable is strength, and it's measuring the compressive strength of concrete. It's measured in megapascals. And to just give you an idea of the units, it ranges from about 2 to 82 in this data set, with an average of about 35. Our predictors are different components of concrete, such as cement and water. And we also look at the age of the concrete, which is in days, from 1 to 365. So we really just want to find out which components of concrete are making it strong. And this data set, like I said, is publicly available. It's on the UCI machine learning repository. And I can actually just show you how easy it is to find. It's right here. It tells you all about the data, number of instances, number of variables, if there are any missing values, and where exactly it comes from. You can even see some papers that the professor that I mentioned wrote about this particular data set. We will be sending you this data set in a follow-up email too, so you can try this out for yourself. So I'm going to go ahead and open up the software now and show you a baseline regression model that we can compare our results to. So what you see on the screen is Salford Predictive Modeler. We call it SPM. This is our GUI. We also have it in a non-GUI version if you prefer to code from the command line. What I'm going to do first is open up our data set. So just click this folder to open up. And I locate the data set, which is called Concrete. It's an Excel spreadsheet, but our software supports the import of all different types of files, as long as it's a flat file with rows and columns. I'm going to go ahead and click Open. So what pops up here is our activity window. To the left, you can see the list of variables that I told you about already. And to the right, you can see statistics about the data. There are 1,030 records and 9 numeric variables. And down at the bottom here, we have a dashboard of activity buttons. You can simply view the data in a spreadsheet. You can run summary statistics. You can create graphs. You can look at correlation, do some data prep, set some options, and score this data on a model, or you can create a model. Now we'll be creating a model, but first I just want to show you what the data looks like. When I click View Data, it brings up a spreadsheet. You can see all the variables are continuous, including strength on the end, which is our target variable. Okay, so I'm going to set up a model now. So I'll open up that activity window again, and I'll click the model button at the end. So this model setup window is pretty much the same for whichever engine you're running, and all you have to do is pick which algorithm you want to use on your data. So this is a list of all the algorithms that we offer, but for now I'm just going to run a simple regression. Next, I have to make sure I select the predictors that I want to put in the model. So in the target column, I'm going to pick strength, and I'm going to select the remaining variables as my predictors. Now, depending on which engine you select in the model setup window, the tabs at the top of the window will change. And these give you a bunch of advanced features to make your model exactly how you want it to be. But with regression, there's not a lot of options here. So we're going to click testing, and we want to make sure that we're not doing any testing, since this is a common practice with a standard regression. You're just setting up an exploratory model using all of your data. So then all I do now is click Start. And pretty quickly, we get regression results. Now this window has our first tab, which is called Summary. It's a lot of statistical measures about the model, including MSE, MAD, R-squared, AIC, BIC. For comparison purposes, I'm going to pick two of the more popular measures that people use in regression, which is MSE and R-squared. So as you can see, our MSE here is 107. And since that's mean squared error, our mean error is around 10. So we're about 10 off with this model. And our R-squared is about 62%. Now for some of you, that might be a great model, but knowing what I know about this data set, I know we can do a lot better. Okay, so next, I'm going to show you our results table. So this is where I'm going to fill in the comparisons of our three solutions against our standard linear regression. So like I said, we have an MSE of 107 and an R-squared of about 62. So our first solution is MARS, and MARS stands for Multivariate Adaptive Regression Splines. And this is a nonlinear, non-parametric procedure. And as you can see in the two pictures at the bottom, on the left, you're fitting a straight linear regression to this scatter plot of data. It's going straight through the data. But to the right, you can see a much better fit using MARS. And these are little knots that the arrows are pointing at, and they're imposing local linearities on this data. And with these knots, we're getting separate segments of lines, which we call basis functions. What this is doing is it's helping explain that variable a little bit better than the straight line on the left would. So this will still give you a regression equation. You just won't be getting the standard variables in your equation. You're getting basis functions instead. So I'm going to show you this in the software. And like I mentioned before, I'm not going to deep into the theory of this because I want this to be a more hands-on demonstration where you can really see how this model is performing on data. So I'll switch back over to SPM. I'll open up my model setup window again, and I'll choose MARS as my analysis engine this time. I'll double check that up here my target type is set as regression because we also support classification and logistic binary, but our target variable is continuous, so we'll stick with regression. Our variables are still selected over here from our regression model. I'll click the testing tab again, and this time we are going to do cross-validation for our testing method. And this is because we do want to see how our model is performing on a separate test sample. For those of you that don't know what cross-validation is, it's a very typical and commonly used method that separates your data into a number of folds, and here we're doing 10 folds. And so what this does is it takes 9 of the folds and builds the model, and then it tests on the 10th fold. And it does this 10 different times, leaving out a different part each time. So essentially you're using the entire data set for training and for testing. One last tab I'm going to look at here is options and limits. As I've said before, basis functions are what MARS is using to impose local linearities. And here the default is 15, but I'm going to increase this to 40 because we want the variables to be able to move around as much as possible so we can get as much information about how they're behaving over their entire range of values. Note that beneath this option is maximum interactions. Here we just have 1, but you can increase this to 2 if you would like to see more interactions, and I'll do that after this run. I'm going to go ahead and click Start. So this runs pretty quickly as well, and what it gives you is a MARS results window with a graph of how many basis functions are in the model against the generalized cross-validation measure, or the MSE. So at each step, MARS built a model with a certain number of basis functions until it reached the optimal model, which turned out to be 28. So we're going to open up the summary again to compare to our regression model. Here, our test MSE is 34. And this is a huge improvement to the 107 that we saw with the standard regression. We're also getting an R-squared of 88%. So I'll go back to the slides to remind you how much of a drastic increase this really is. We're going from about 10 mean error to a little under 6, and our R-squared is increasing by over 20%. Now, I told you about the interactions in the Mars. So we only started with 1 here, but we can increase that to 2. All we have to do is go back to our Options tab and go to 2. Click Start, and this will build a brand new model with 2-way interactions. So with our first model that we built, we're getting test MSE of 34. We can also look at our variable importance in that model. So this is what we really want to know. We wanted to know about which predictors are contributing to the strength of concrete. And here we can see that our most important variable is age. Our second most important variable is cement, and the least important is coarse aggregate. So how exactly is age contributing to this model? We don't know if it's better for it to be really old or better for it to be young concrete. So this is how we find out by clicking this basis function. Like I said, if you prefer a regression model, this is where you can find similar output. You have your y equals model with your intercept, and then you have all of your basis functions in here with coefficients. Now these basis functions are the piecewise functions that I showed you in the graph. For example, basis function 39 here is the maximum between 0 and fine aggregate minus 943. So if you really want, you can go through and calculate this yourself so you can really see how it's working. Otherwise, you can take a look at the plots that come along with Mars. These are the 2D plots since we only have one-way interactions. And when I click Show All, you can see each individual variable plot. So for example, age in the upper left corner. If a standard regression was just running a line right through this age graph, you would think that the stronger concrete is the older concrete. But actually, at about 50 days, this graph plateaus. And so the concrete at 365 days is just as strong as the concrete at 50 days. So this is telling you a lot more than a standard regression would. And the same goes for the other variables in the model. You can see water in the bottom left corner really jumps around on the plot. And you can see that fly ash has a steep increase and then suddenly drops off at the end. Now, how does this differ when we add interactions? Here I have my third results window that includes 2-way interactions in the model. And as you can see, we now have 38 basis functions. So it added 10 more basis functions when we upped the interactions. Our summary shows that our MSE did decrease a little, and our R-squared went up about 2%. Now, instead of 2D plots, we have 3D surfaces that show the interactions between all of the variables. These can be kind of cool to look at if you're interested in how each predictor is interacting with the others. Okay, so we're going to move on to the next solution that we have, which is TreeNet. And TreeNet is also known as stochastic gradient boosting, or GBM if you're using R. And what this is small decision trees that are built in an error-correcting sequence. So first we start with a small cart tree, which you can see as tree 1. When I say small, I mean that we usually grow it to a maximum of 6 terminal nodes. So those blue and red color-coded nodes at the bottom of the tree are the terminal nodes. We only want to reach about 6 of those. And the reasoning for this is because we're building a lot of these trees. We usually build about a minimum of 200 trees. And so it goes much quicker if the trees are kept to a small size. And we've also found that it's all we need to grow it to the size to actually extract all the information. So we grow this first small cart tree, and then we compute the residuals from this model for all of the records. And we grow the second small tree, tree 2, to predict the residuals from the first tree. And we keep doing this process. And what happens is it approaches the best solution. So like I said, we grow a minimum of about 200, but sometimes we have to grow up to about 30,000, depending on the data and how fast it's learning about the underlying relationships. So at the end, we add the sequence together to find the final prediction. So now I'm going to show you how to run the concrete data model in TreeNet. I'll close out of some of these windows just to reduce some of the clutter. So we're right back to the model setup window. I'm going to change the analysis engine to TreeNet. Make sure all of our variables are still selected correctly, and we have regression as our target type. We're going to do tenfold cross-validation again. We also have a TreeNet tab in this model setup. Now this gives you a lot of different parameters for setting up your TreeNet model, such as loss functions. We're going to use the default here. And that's another thing about the software is the defaults are meant to give you good starting points for running the model. So you could just pick your variables and click Start, and you'll get a pretty good model, and then you can tweak the parameters afterwards. We also have overfitting protection and limits for the tree. Here is where you'll see the 6 maximum nodes per tree that I mentioned before. Now the number of trees to build is set at 200. I'm going to increase this number to 500 for now because I know from trying that this model does need more than 200 trees to reach a good result. Finally, I'm going to turn on some plots because we've got the plots with Mars, so I want to compare those. We have both 1 variable dependence plots and 2 variable dependence plots. And to keep this simple, I'm just going to use the top 3 variables. So now I just click Start. So this is building 500 trees, but as you can see, it goes pretty quickly. And the cross-validation is being computed in parallel. So here we have our TreeNet output. And what you get is a graph of the number of trees built against a performance measure. And here we want to look at MSE. So like I said before, 500 trees still isn't enough for TreeNet to get to the optimal solution. So in this case, you would increase the number of trees and keep trying. But for the purposes of keeping this webinar quick and easy, I'm going to leave it at 500. I can bring up the summary statistics again so we can compare it to our other models. Our MSE for the test sample is 31.8, and our R-squared is about 89%. So this, again, is a huge improvement over our standard regression model. As you can see here, I'll just show you quickly in comparison. It does a little better than Mars, but I'm not comparing it to Mars, really. I'm just comparing it to the standard linear regression. And again, we're going from about 10 mean error to between 5 and 6. So TreeNet, just like Mars, has some cool features. You can look at variable importance. Again, we can see that age and cement are the most important variables in this model. You can also see different things in these tabs, like outliers. It'll alert you in green to outliers that are taking up a large percentage of the MSE. Or you can look at box plots of the residuals. But I also want to look at those plots that I created in the model setup. I'm going to come down here and click Display Plots. This will bring up a list of all the plots that I created, one variable and two variable dependents. I'll click Show All. So first I'll take a look at the one variable dependence plots. Now the way these partial dependency plots work is you're plotting the predictor, such as age, against the contribution that that predictor is having to the target variable. So here you can see that in the first 10 or 20 days of the concrete, it's having a negative contribution on strength. And then it crosses over to a positive contribution where it plateaus around 100 days. With cement, it's having a negative contribution to strength until about 250 units, where it starts having a positive contribution to strength. And with water, you're seeing a slow decline. So the more water, the weaker the concrete. We also created some 3D plots showing the interactions between variables such as age and cement. You can open these up. You can move them around, which is kind of cool to look at sometimes. You can turn it into a heat map if that's how you prefer to look at things. Okay, so we have one solution left to look at, and that's random forest. Okay, so random forest is an ensemble of trees, just as TreeNet is, but it is built on a bootstrap sample instead. So what bootstrap sampling is, say you have a bag of all of your data. So we have all 1,000 or so records in a bag, and we want to build a model. What we do is we pick out a record from the bag, write it down, and we put it back in the bag. So this is sampling with replacement. So the next record you pick out could be the same record you just picked, or it could be a totally new one. So the point is that you may be picking records more than once, and you may not be picking some records at all. So how the algorithm works is each tree is grown on one of these bootstrap samples from the learning data. And then as you're growing the tree, which is the cartridge that I showed you a picture of in the TreeNet model, at each node that you are creating, you're only picking a certain subset of predictors. So if you have thousands of predictors, this is really speeding up your process by randomly selecting P of these predictors. And by default, a good value for P is the square root of your total predictors. So with TreeNet, you would add up your ensemble of trees to get your final prediction, but with random forest, you're actually averaging over all of the trees. And you may be thinking that if you're randomly selecting predictors at each node, what if some predictors aren't getting used in a tree? And this problem is solved because you're growing a whole ensemble of trees, so the predictors will show up at some point in your ensemble. And when you average them, you're really including all of the information from your data. And we're ensuring convergence by the law of large numbers. The more trees you build, the quicker that your model is going to converge. And the key to accuracy here is low correlation and bias, and that's through a subset of predictors. And the difference here between random forest and TreeNet is that we aren't growing trees just to 6 terminal nodes as we did in TreeNet. We're actually growing the trees to their maximum depth. So this could take possibly a little bit longer than TreeNet would. So I'll go back to the software now and show you how to run a random forest model. I'll open up my model setup here, and I'll change the analysis engine to random forest. Make sure everything is still okay in this window. Now our testing tab shows us something a little bit different. For random forest, we're using out-of-bag data for testing. Now, like I described before, when you're sampling with replacement, some of the records in your bag of data aren't getting used at all. And so this is sort of a built-in testing sample. So why would you use another partition to test when you can just use those records that were never picked in the first place? And as you can see, we don't even give cross-validation as an option for testing here because out-of-bag data is the common practice. We also have a random forest tab here where you can change some of the tree limits. Number of trees to build is 200, and that's fine for now, but you can increase this. And I'll go ahead and click Start. So here we get our RF results window, and this is the number of trees grown against the MSE. So random forest tracks as it builds each consecutive tree what the MSE is doing. So you can see it continues to decrease here. Like I said, the law of large numbers ensures the convergence in this model. I'll click the summary button again to bring up the MSE and R squared. In OOB in this column, instead of test, stands for out of bag. And our MSE is 25.53911. So about mean error is down to 5 now. And our R squared is up to about 91%. So to go back to our results table, this is the best model we got with random forest. And again, I'm not comparing among our 3 solutions here. I'm still just comparing to the standard linear regression baseline model. And we've seen a huge improvement. And these model measures can vary. If you grow more trees in TreeNet, if you use a different number of basis functions or interactions in Mars, you're going to change these values. But if you do exactly what I did, this is what you should get. So this is only one application. I just showed you a civil engineering application with the concrete data. But we have a lot of different users of our software. For example, we do epidemiology. We have prostate cancer diagnosis, use of our software. We can do real estate housing values, ecology, public health. And we actually want to know what you guys are using, and we want to know what your data looks like. And if you ever do need help with building models with your data, we want you to send us your data. And we can either use it for a webinar or a meeting with you to show you how this really does improve greatly on your regression. So before I take any questions, I just wanted to say that support@sulfur-systems.com is where you should email with any additional questions or problems that you have with the software, or if you just need help with building your own models. And you will be getting a follow-up email that will have a recording of this webinar. It will also have download instructions for a 30-day trial of our software. And I've put together a tutorial of exactly what I did in the webinar today, and we'll be giving you the concrete data set so you can try it yourself. And we have data mining trainings throughout the year. Our next one coming up is in New York City, March 18th through 20th. And that'll be a more in-depth look at these algorithms. So if you do want to see some of the theory behind them and not just the hands-on demonstration, then that will be the place that you should sign up for those. And we'll have information about that in the email that we send out. So I'll take a look at some of the questions now. Okay, so the first one are, what are the units of measures of the components of the concrete? So I'm not an expert in concrete, so I can't tell you off the bat. But if you do go to the website for the UCI machine learning repository where the data set is located, it'll give you a little bit more information on these variables. So as you can see, cement is measured in kilograms. Most of them are. And age is in days, and strength is in megapascals. So all the information is there. And it's easy to Google if you just Google UCI concrete. What are MV and LSTAT? So those are two examples that I gave on this slide here in Mars. It's a different data set of ours for housing values, median housing value, and percent of lower socioeconomic status. And it was just a good example of a straight line through a scatter plot of data and then a nonlinear regression through that same data to show you the knots. So that was purely for an example and wasn't related at all to the concrete data. One of the questions is, can we get all the same functionalities with scikit-learn? I'm not familiar with these exact algorithms in Python, so I cannot give you a definite answer on whether all of the same functionalities are available, but I do know that our software has some of the best computational accuracy and speed, so I doubt that you will be able to get the exact same results in Python. Are the basis function plots interpreted the same as partial dependency plots? No, they are not. As you will notice, the basis function plots did not have negative values in them. So the partial dependency plots are looking at negative contributions to the target values, while the basis function plots are not. Another question is, can the software handle R scripts? So what we're working on now is an integration between SPM and R that will allow you to call the software while you are inside of R. So that's something that is currently in development right now, and we are hoping to roll out in the near future. Where have you seen Mars produce better? Is one of the questions. Oh, yeah. So what we recommend is sometimes you just have to try out these three solutions, and you're going to see different results depending on the data you're using. So for some instances, like if you have wide data with a lot of outliers, then random forest may work best for you. If you're looking in something that has a lot of nonlinearities, Mars might be the best because you can increase your number of basis functions. Typically, there's just no definite answer about when something will perform better. You just have to try them out with your data. Okay, sorry, I'm reading through the questions. SPM works only on Windows. Currently, it works on Windows and Linux for the non-GUI, but if you install Parallels on your Mac, you will still be able to use SPM. Can you automate this process in a script to explore various settings of each modeling technique? The answer is yes, and I can show you that in the software. So in our model setup window, there's a tab called Automate, and in the version you have, or that you will be downloading, it will be called Battery. And in total, for each modeling engine, there are 75 different mini automation suites. And what this does is it gives you the option to automate maybe a certain parameter. This one here, I'll give you an example. It's called partition, and you can set up a learn and test partition, and then you can have it repeat as many times as you want to bring up results of all of those models. And it goes pretty quickly, and then you can compare them easily to each other. And you can do that with most of the parameters, such as in TreeNet, you can vary the learn rate or the maximum number of nodes per tree. And you can choose as many values as you want, and you can repeat it so that you can compare, and it'll actually give you a graph and whatever measure you want to compare against for all of those models. How well would a pure cart regression perform is one of the questions. I can actually show you that in the software. All you have to do is change the analysis engine to cart, and I'll pick cross-validation for testing, and I'll click Start. So as you can see here, we got MSEs in the 50s and 60s and R-squareds in the 70s and 80s for these models. I still had the partition automation set in there, so that ran this 10 times. And so CART still does perform better than a regular regression, but not as well as some of our other solutions. What is 1 versus 2 interactions for Mars? So as I showed you, switching between 1 and 2 interactions gives you either 2D plots for your variables or 3D plots. So then you're adding in the interactions among the variables themselves when you change it to 2 interactions, such as between age and cement. If you think that those 2 variables are affecting each other in some way, you can add that into your model as well. How you are measuring importance of the variables is one of the questions. So variable importance ranking is done by seeing, for tree models, it's done by seeing how many times the variables are appearing in the ensemble and how much they're contributing to that. And then the importance is scaled so that it's relative importance. So when you see 100% of one variable, that was scaled relatively, so you can see how in respect to the other variables in the model. If we test these tools, these 3 tools on other data, random forest is always better, is one of the questions, and that is not true necessarily. Depends on the data, depends on the structure of your data, how many variables you have, what kind of relationships are hidden in the data. You're going to get different results every time. So there's no saying which tool will be better on other data. Okay, sorry, I'm reading through some of the questions. I've already answered some of them. Where to find out the final algorithm for future scoring is one of the questions. So I can show you. For example, for our random forest model, down here you have a set of buttons. We have commands where you can get the command file that built this model. Translate. What this button does is you can pick a language. We have SAS, Classic, C, PMML, and we have Java and topology supported in some of the engines. And what this does is this will translate the model that you just built into any of these languages pretty quickly and easily. You can also score your model here. You can either score it on new data or you can score it on the data set that you used to build it and save your results as any type of file you would like. And additionally, we have a save button down here where you can just save this grove and open it up again anytime you want without having to rerun the entire model. Another question is, you get a different ranking of the impact of the input variables according to the different algorithms. And the answer is yes. They are very different algorithms, so they are ranking the variables in a different way. In addition, if you build a CART tree and a variable is important in that one tree, once you build an ensemble of trees, as in TreeNet or random forest, you have to average that importance over maybe 200 trees. So the importance rankings are going to change. When you're bootstrap sampling for random forest, for example, one predictor may not be included in every single tree. So the importance is going to average over all of those trees, and it will change with the different algorithms. Are there restrictions on the data set size that can be analyzed? We do have different licenses of different sizes that can handle different sizes of data sets. It depends on how big your data is, because we don't want you to pay for a license that has an unlimited data capacity if you're not using such a large data set. But as of right now, we haven't seen any concrete restrictions on data set sizes. Can you code these procedures, or does someone have to use pull-down menus? Yes, you can code them. We do have a non-GUI version of this. That's all command line. In addition, you can use this classic output window in the GUI to code things by hand if that's how you prefer. How is the software different from SAS is one of the questions. Like I said before, we have documented advantages in both speed and accuracy with our software. And we do have this GUI version that gives users quick and easy results without having to learn a lot of coding. Another question is, were there missing values in your data? The answer is no. It was hard to find a data set that was easy to understand, that had all of the problems of a regression. But I can tell you that missing values are very well handled in all three of these solutions, and that's something that you can try yourself, or that we can have a future webinar on how to handle. Could you show me again how I can find the contribution of each predictor on the target? Okay, so that's where the TreeNet partial dependency plots came in. So you just have to click Display Plots at the bottom of your TreeNet window here. And what that does is it brings up these partial dependency plots where the predictor and its values are plotted against the contribution that it's having on the target variable. Some of these questions are about pricing and more about the theoretical algorithms behind the software. So we will be answering those outside of this webinar because they are specific questions depending on your needs. So any of those questions that you might have, feel free to send them in to our support at Software-Systems, or we can get back to you on those after the webinar has ended. Another question is, how do you handle categorical variables? So the model I just showed you happened to have all continuous variables, but categorical variables are handled just the same. All you would do is in the model setup here is you would check in the categorical column if your variable is in classes instead of continuous. If there are character variables, that will be automatically recognized and that box will already be checked for you. Do all the models easily handle a mix of continuous, categorical, ordinal variables? It's a related question. The answer is yes, they do. Can the software produce an equation for the best or any model? The answer for Mars is yes. I showed you where the basis functions tab can give you an equation for the model. For TreeNet and Random Forest, it's kind of a black box, but you can do a SAS translation like I showed you. If you translate into several different languages, then you can better see how the algorithm is actually working, but we cannot give you an exact equation for that. How would you choose which final model to use? Would you only base it on R squared? I would say no. You can choose which final model depending on which engine you prefer. Some people want the regression equation of Mars. Some people want the partial dependency plots of TreeNet. There are also a lot of other measures included in the model building, such as MAD or MSE that you may want to look at instead. And we like to think that we give the user the option to make those decisions themselves. We just give you all of that. In CART, you can penalize high-level categorical variables, but not in Random Forest. That is correct. There is no penalty tab in the Random Forest engine. And This is because random forest does a different predictor selection technique, whereas I told you before, it's only selecting a certain subset of predictors at each node. So in this case, the penalty might not come into effect. It might not be chosen at all. How many variables maximum can Mars handle? So we base our data capacity on number of data cells. So we're also going to take into account how many records are in the data set. And we have an entire chart on the scalability of all of our engines that you can email support for the link to that information. Another question is, can we have a copy of the presentation slides? That's something we'll have to decide if we will put in the follow-up email. But we will have a recording of the webinar, so you can always watch that to see the presentation slides. Our software does not use neural net. We have a couple more questions on categorical predictors that I already answered. It looks like we do have a few repeat questions and questions that will have to be handled as part of our support team because they have to do with pricing and software limitations. So I think we'll end the webinar there, and then I will get back to the rest of the questions that we have here. So thank you guys for joining us. You'll be getting a follow-up email with all of the information that I told you before, and I hope you enjoyed the webinar.